start recording now. Okay. Yeah. Could you see my screen, share screen?
Yeah.
Yeah, this is the first question. Compare strings by frequency of the smallest character. Two array of string are given, and we will calculate the frequency of the smallest calculate in S. For example, if S is DCCE, then the FS is 2, because in the DCCE, C is the smallest character, and the frequency of C is 2. So the FS is 2. Now, given string arrays, queries, and words, return an integer array answer, where each answer I is the number of 2 words such that F query I less than FW, where W is a word in words. Yeah, this description of the question a little bit longer. Yeah, but let's go through the examples. Yeah, the example 1, the two string array, one is queries and another is words. Let's look at the queries string array. It's CBD. In this string, C is the smallest character, and the frequency of the C is 1. So the CBD string has a 1 value. And for the word array, there is 1 string here. The smallest character is A, and the frequency of the smallest character is 3. So the value of this string is 3. Yeah, for the answer array, we have to return the number of the integer. That integer means the number of the words such that F queries less than F words. Let me see, because the frequency of the CBD is 1 and frequency of the ZAAAZ is 3. So the frequency 1 is less than frequency 3. So the answer is 1. Because there is one, there is a one number satisfies the condition here. So the answer array has the 1 element value here. Yeah, we can look at another example. There are more strings in the array. Yeah, like the example 2. The queries had the 2 array. One is BBB and another is CC. We can see for the BBB, the smallest character is B and the frequency is 3. And for the CC, the smallest character is C and the frequency is 2. For the word string array, there are 4 strings. One is A, and another is A. Let's find out the frequency of these words. For A, the frequency is 1. For AA is 2. For 3A is 3. 4A is 4. Yeah. Let's look at the answer question, answer array. For the first string BBB, the value is 3. So there is only one string in the word. It's a words array. It's the queries array. In the words array, there is only one bigger than 3. So the answer for the first string BBB, the answer is 1 here. For the second string in queries, there are 2 words in words array bigger than 2. So the answer is 2. Is that clear?
Yeah.
Yeah, the process is to find the smallest character frequency and compare 2 array of string and return how many words in words array are larger than frequency of the word of the string in the queries. Yeah. Any idea for this question?
My my idea is to find the frequency in the word list, so we can pre-process the word list and get a list of frequency. We can go through it and find the like, you know, an array. We have an array of integer, right, where each element is a frequency of that word at that index, and then we can iterate through the query and then find the frequency in each query and do the binary search on the on the frequency list. And, you know, maybe the frequency list, we have to sort it first.
Sort list.
Yeah.
Yeah. And iterate the list of the frequency.
Queries, yeah.
Yeah, yeah. Queries frequency, yeah, list. Yeah.
Then that means we can map this problem into a binary search, right? As long as we can find the frequency of each word in the list.
Yes, that will have the complexity of log n. Yeah, but if you use the binary search, yeah, to catch how many elements are larger than the query frequency. Yeah.
Yeah.
Yeah. Anyone has other different approach? Yeah. If not, I could see. Yeah, I really use that approach to solve this problem. Yeah. Maybe I can go through my code to share.
I have another approach.
Oh, yeah, yeah. Yeah.
So I don't apply the binary search because could you short down the condition of the problem? They have like they mentioned like the maximum length of the string is 10, right? So the maximum length of the string is 10. So that means the frequency, the maximum frequency, also maximum of frequency will be 10, right?
Yes, yeah.
So we can create the array have a length of the 11. The reason the length 11 because they start from 0 into 10 because they include from 1 to 10, right?
Mm-hmm.
So we use that array to calculate, like, for example, at every index, that means like the number of word, the value at every index is the number of word have like the frequency equal with the index. For example, we have the array at 3 equal 5, so that means we have a 5 word have a frequency equal 3.
Mm-hmm.
And then when you travel through the varies and you have a word in the varies, and you calculate the frequency of that word, and then because we need to find the how many word have like the frequency greater than that word. So for example, we find the CBD have like the frequency will be 1, so that means we start from the index equal 2 in the array we have already make by on like the list of word. You remember I make the array have a length of the 11, you remember that one? We start from index 2. Index 2, that means we start from like calculate how many word have a length start from 2 until the end, and then we use the one variable and to counting that one. So that means because we have the array have a length equal 10, so that means every time we travel that array, so they will take only the time complexity will be 01. So that means we don't apply any binary search here. And and I think the time complexity of this one will be ON plus M with N in the length of query and M in the length of word.
Yeah, in this, I think this approach, we could also do the pre-sum, right? One, you calculate the way that you describe, and we can do the pre-sum. So, you know, we go in that index, we know right away, like how many is, you know.
You can do it because the length of the dash one only 10, so even we don't do pre-sum, it's okay. But yeah, you can do pre-sum.
Yeah. Could you take some examples for this input?
Okay, sure. For example, first one, I don't take care the varies. I take care the word, and I create the array have a length equal 11.
Okay.
For example, array have a length 11.
11.
Yeah,
11 length word.
the length of array. Yeah, length of array. Array have a length of 11.
Okay.
Yes.
Array.
Yeah. So that means the value of that one start from 0 into 10, right? The index start from 0 to 10.
Yeah.
Yep. And I go through every word in the words array.
In this array.
Yes. So, and for example, the first word will be A. I have the method to calculate that the value of that one. The value of that one will be 1. Yeah. So that means the value of that one will be 1. So that means array at index 1 plus 4 1. So that means I will have an array at 1 will be equal 1.
Let me see. There is an index for that.
Yeah. 4, 5, 6, 7, 8, 9, 10. Yeah. So array of 1 will be equal 1.
Array of the index 1.
Yeah, array of the index 1 is 1. And same formula. So array at the index 2 will be equal 2. Array at the index 3 equal 3. 4 will be 4. Yeah, we done.
Array, the index 2 will be 1, right?
No, index.
For the index 2, the value will be 1 because you are having a single word right now with frequency 2, correct?
No, it's free. Yeah, sorry. I'm sorry. 2 will be 1. Sorry. I forgot.
No problem. Yeah.
Sorry. Yeah, and 2 will 1. Yeah, and 3 will be 1, and 4 will be 1. Yeah.
Yeah.
And now we go through all the varies, and we have like BBB, and then we calculate the frequency of BBB will be 3, right?
Yeah.
No, we don't flush on that array. But
actually, as I think Leon said, right, we need to do a pre-sum first on this array, the 11th length array, right? Then you actually start the queries. Is that not what you're thinking about?
In my implementation, I don't do pre-sum, but yeah,
Okay.
but you can do pre-sum.
Oh, no problem. So let's go with your implementation. That's okay. Yeah.
Yes. So we go through every word in the query. So from BBB, we have we can calculate the frequency of that one from equal 3, right?
Yeah.
So that means in the array, 11 length array, we start from index 4, right? Because
yes.
we start in index 4 until 10. So that means we use the one variable to sum that one to aggregation at that one. So we have when we have
one here.
One here, and same situation, we have a CC equal 2. So that means we start from index 3. So that means we have the value at index 3 will be 1, value at 4 will be 1. So we flush that one will be 2. So that means because the problem is they give the condition the maximum length of the word will be equal 10. If they give the maximum length of the word will be a loss, so we cannot do this one. That based on the condition.
It's like the constant or something. Yeah, you just put value into the index.
Right.
Yeah. Good.
Yeah, and pre-sum, you can for sure you can do pre-sum, but on when I implementation, I don't do pre-sum.
Yeah, it makes sense because it's just a length of a level.
Yeah.
So it's okay to do this way too.
Yeah.
So I have one question, like what is mean by pre-sum?
Pre-sum for this 11 length array, it's like the pre-sum is to the first k, sum of the first k element, like the sum of the first one element is 0, and this is 1, and this is 2. 1 plus 1 is 2, and 2 plus 1.
No, I would do the reverse way. I would start from 10, like when I come to 4, it will be 1. When I come to 3, it will be 2. So if I go in the reverse way,
Reverse way?
Yeah.
Okay.
So for the 4, 1, and 3, it will be 2.
This is 2.
Yeah.
It's
and this
3.
Will be 3. Yeah, and this will be 4.
This is 4.
So whenever you look at the query and find that and in this index, so you find that element, and that's the value. Yeah. Okay.
Yeah.
So this is the sum of frequency or actual value of the element in the array?
No, it's the sum of frequencies.
Oh, yes. Okay. Then I got it. Thanks.
Yeah, if you use the pre-sum, you just get the value immediately. You needn't to go through from 3 to 10 to sum them up. Yeah, is it correct?
Yes.
Yeah. Yeah, it's
if you do the reverse sum, let's say if they query let's say they query at index 0, then how you know what the answer is? It's not feasible, but right? Yeah, it's not feasible. But suppose that we ship the reverse prefix, forward, and now if suppose that at index 1 it's 0, then how you know what would be the answer?
So for 0, you need to make it 4. She didn't complete that.
Yeah.
You have to do it till the end.
Yeah, but
that's okay. Yeah.
0 is impossible because at least there is not an empty string.
Oh, okay.
Yeah, because you have at least one frequency.
Yeah.
Yeah. Is there any question on this? If not, I'll move to the next question.
Yes.
Can you quickly run through your code? I'm interested in looking at the binary search the way you did it.
Okay. Yeah.
Just quickly run through it. Yeah.
Okay, that's not the best solution.
It's okay. It's okay.
It's okay.
Yeah. Okay. My implementation is like the first approach to calculate the two arrays frequency and put them into a list A and B, and sort the list of the word here. Sort the list of word. Sort the B. B is the frequency of the string in words array, and then I just iterate the every element in A. A is the frequency of the query array string, and binary find the its value. That is how many numbers are greater than the frequency of the query words. Yeah, it's just get the number and put it to the output array. Yeah, that's yeah. It's not the time complexity could be n log n. Yeah, it's not all of n. Yeah.
Okay. Okay. So you're using the upper bound, and that is what it does the binary search here, right?
Yeah, yeah, that's the binary search. Yeah. Maybe if you use other language, maybe you will write the binary search, have the left and right, and while left less than right, and you find the middle point. Yeah, and the middle point left or right, depend on the median is larger than your target or greater than your target. Yeah. Yeah.
Yep, good.
Okay, I'll move to the next question. Yeah. This question is a delete a node in a binary search tree. A root of node of the binary search tree and a key that the key value is the node we would like to delete. Yeah, with that key in the binary search tree, return the root node of the binary search tree. That means return the root that you already delete the target node. Yeah. And this is a binary search tree. So that means the left node always less than the root node, and the right node is always bigger than the root node.
Okay. So you're trying to say that we have to delete a node with the key value.
Yeah.
And then return the root, right?
Yeah, return the new root maybe. Yeah.
Yeah. So yeah, if it is okay, and then we are given a thing. Okay, it's a binary search tree, so it will be ordered. Yeah.
Yeah.
So
it's a binary search tree.
So you can just do everything in the O of height of the tree. That is what the time complexity says in the node.
Yes. Yeah.
Right.
Yeah.
So it is inherent. So we don't have to do anything special for that. Yeah. Okay.
Yeah. That the deletion can be divided in two stages. One is search for the node. Yeah, the search for the node with the target value, the key with the key. And the second step is to delete that key, that node. Yeah. Let me look at the example. There is the binary search tree. We can see every left node is smaller than the root node, and every right node is bigger than the root node. So it's a binary search tree here. The target value is 3. That means we have to find the node with the value 3 and delete that node. Yeah, we can see there is a node with 3 value. We have to delete that node and return the new return a new tree. Yeah. Yeah. We can see that the new tree. For this tree, the node with 3 value is already deleted, and the next node of the 3, 4 is moved to the position of the 3. So this is a tree we need to return. Yeah, there is another valid answer. Yeah, if we delete 3, there is 2 ways. One is move the left node of the 3 to the position, or move the right node of the 3 to the position. So either way, yeah, is a new binary search tree. Yeah. Every left node are smaller than the root, and every right node bigger than the root. Yeah, we can see both of binary search is valid. Yeah. So, yeah. First, it's a binary search tree, and we also have the key value. The key value is the node with that key value is to be deleted. From the example, we can see when we delete a node, first we'll find the node with key value, and the second step is delete the node. When we delete the node, what could we do to move the left and left subtree and the right subtree of that node? Yeah, we have 2 ways: move the left subtree or move the right subtree to that position.
So suppose if we delete 5, like the root node, and in this case, either left subtree or right subtree, right? Which one would be preference?
Yeah, if we delete the 5, yeah, I think the 5 is gone. We can move the 6 here.
Your minimum element from right side. Yeah, it's correct.
Yeah. And another way is to move the
4.
left. Yeah. Move the 4. Yes. And this one. Yeah. Think about when we move the 5. The 5 is my target node to be deleted. What's the next node of the? For the right tree, 6 is the next node. For the left subtree, 4 is the previous node. Yeah, that means when we delete the target node, either I can move the next bigger node to the position, or move the previous node to that position. Yeah, is it clear?
Do we have to keep? Do we have to keep the address of the node, or can we just swap the value? Would it be okay?
Swap the value. Swap.
Yeah. For example, in 4 and 5.
4 and 5. Yeah. Okay. For this one, it's 5 here, and it's 4. Okay. Yeah. We swap the 5 and 4, and then we can delete the 5. Is that your approach?
Yeah, in this example, that's how I see it.
Yeah. Yeah, swap and delete the leaf node. Yeah, because when you delete the leaf node, you needn't move its subtree. Yeah, because it's a leaf node.
Yeah, but in case of 5 and 6, it doesn't work, right? Like I cannot swap it and delete it.
Yeah. If you deal with this situation, yeah. If you swap 5 with 7, yeah, it doesn't work. Yeah, because the 7 is not the 5 next node. You have to swap the target node with its previous node or next node. The previous node means that that's the maximum node less than 5, or the smallest node larger than 5. Because when you delete a node, you have to keep the tree a binary search tree. Yeah.
Simply, I think we can do in order traversal and pick the next greater element. I mean, you'll get a sorted array because it's a binary search tree.
Yeah, in order the traversal, and
you'll get a sorted array in this case.
Yeah, it's a binary search tree. It's always sorted. Yeah, root and right. Yeah.
We can
but if we do the in order traversal, that's gonna be worst case gonna be big O of n, right?
Yeah, here also I think big O of n only, order of height it will take.
I think the question was asking for, was it like
should be
high of the tree, log n only.
So in that case, we can't do in order, right?
Yeah. So maybe we go case by cases, you know. Let's say if the delete node have only one child. Yeah, child. And what we do. And if the delete node have 2 child, and what we do. And if the delete node is a leaf, and you know what we do.
In case of leaf, I think we directly need to strike out. It will not affect the tree.
Right.
And in case of having only one children, simply you need to put it. That will also not. But the problem arises when we have 2 children. I mean, that's not which you want. So in that case, if you are on the right side, you take the minimum element from there. And if you are on the left side, take the maximum element from there.
So let's say we add to the 6, we add a left child. Let's say
5.
Instead of put 6, put 7 there. Put 7, and then instead of 7, put 9, and then 6. Okay, no, 5 is okay there. Yeah, 5. Here we'll put 7. No, instead of 6, we put 7.
Put 7 here.
Yeah, and then here we put 9, and on the left side we put 8. Okay, put 9 here, and left of 7. Left of 7. No, left of left of 7. We put what is it? 8.
How
so if you want to delete 5.
You replace it, I think. 7.
It's only 6. Yeah.
I'm sorry. Yes. 6. I'm sorry. Yeah. So let's say we delete 5.
Yes. Yeah, delete 5. Mm.
So the way we're gonna go, I think, we should go, so right of the one that we want to delete, and then the leftmost child,
Yes.
and then replace
Yeah.
it.
Yeah.
So it's always gonna be right and then leftmost child, right?
Yes.
Yeah.
The right and leftmost child, that means you find the target node next node.
Yeah.
The minimum node greater than your node. Yeah.
But
right
what if the leftmost child have the right subtree? Then what we do?
No, the leftmost child is always gonna be leaf.
No,
it's
it could
not
be have the
No,
right
it can
subtree.
have it. So in that case, what you can do is you can again recursively go and delete that.
Yeah.
No, or we can do the in order traverser on the right side and take the in order successor. Like you will get the sorted in this right side and pick the minimum element from there.
Right. So you'll have to do it a recursive way. So
Yeah.
you'll be doing it in O of height tree or height of tree, right?
Yes.
Yeah.
Okay.
Yeah. If we I can divide it several situations. Yeah. The one situation is only has a root node, just itself, and if the node value is equals the key value, that means I just delete the root and do nothing. And another condition is the key is larger than the root value, and we will recursively call the function. What's the name of the function? Delete node. Yeah, delete node. Delete if the key value is bigger than the root value, that means the node we want to delete is in the right subtree. You just delete the key value. Yeah, is it correct? Yeah, yeah. This I just divided several different situations to discuss. If the key is less than the root value, that means the node we want to delete is in the left subtree. So this is recursively called the delete node. Yeah, and now we can see we have the situation, the key is equals the root value. Yeah, that means we need to delete the root, like the examples we discussed before. In this situation, the key is 5, and we have to delete the root node. In this situation, I think if the root left subtree is none, or the root right is none, that situation is like this is 5 and the left is none. We have the right subtree like this is 6, 7, 7. Yeah, maybe there is is 7, 8, and this has like the 6. Yeah. In this situation, we just delete the root. Yeah, when we delete the root, we have the new root node 7, because this root node has no left subtree. the same thing is if the root node has no right subtree, we can just simply delete the root node and return its right or left. Yeah, that will be fine. The next situation is we have the left subtree and the right subtree. We'll do go to the right node and find the leftmost node.
Okay, so for the first case where you're saying root dash left or root of, left of root is equal to null. No, in the same way, root key is equal to root val. Okay, in that the first one we say left of root is null or root of right is null. But in the example, you are just showing a right side, right?
Yeah.
So then we have to again verify whether it is the right side or the left side and then do this, or?
I think the situation is the same. Yeah, that means if this example is root left subtree is empty, and we can also have this way.
So you'll have to again differentiate coming inside this condition, saying, okay, now I need to check whether it is the left is the not null or right is not null, right?
Yeah.
So why specifically doing this?
That's the simplest situation for the root node. That means it only has one side subtree. Yeah, either it's the left or the right. Yeah, you can separate into two situations, but in my code I combined these two situations into one sentence, so I didn't separate them.
Okay.
Yeah.
So I was thinking, like, why don't we just look at if the root, right of root is not null, then do the one what you did explain.
Yeah.
And then if you do another condition of root dash left is not null, then do the second condition.
Yes.
And then just go for the leave, maybe something like that. Yeah.
Okay, I'll show my implemented code later. Yeah, and
okay, no problem. Sure.
Combine these two situations together. Yeah.
Okay. Yeah. Thanks.
And the next situation is root has a left subtree and the right subtree. We do go to the right node and find the leftmost node. Yeah. Let me show like this. This example, if we delete the 5 has a left subtree and the right subtree, and we go to the right node and go to the leftmost leaf node. Yeah, leaf node, and find the 6 here, and we change the we move the 6 to the root node. Yeah. And delete that. And that's the process to delete the root node. Yeah. Is that clear? Yeah.
Yeah, so just replacing the value, right? We don't need to kind of like rewire.
Replace the value, and then we will recursively delete the value, like if let me see, there is a 5 here and it's a 6. if the 6 also has its right node, like this, this 6.5, like here. When the 6 is the leftmost node, and to replace the value with 5. Is that correct? Yeah. And we have to recursively delete the 5 here.
No, in this case, what is the 6.5 again?
Yeah, and node.
Mm-hmm.
Yeah, the 6 is the leftmost node for the 5. Yeah.
Yeah.
The 6 also has its child. Yeah.
Right child.
Binary tree. It have to bigger
Yeah,
than
but we're
6
looking
and
for the
less.
leaf, though. I mean, if we counter leftmost child that has any children, then we gotta go again right and then all the left. No.
No, I think it's not the leftmost node. It's a leftmost node. Yeah.
Oh yeah.
Yeah. That's my fault. Yeah, it's a leftmost node. Yeah. Maybe I can go through my code and explain how to implement this approach.
Yeah, sure.
First of all, this is a corner case. The node is a noun. I just return noun here. And that's the first situation I mentioned before. The key is less than the root node. That means the node I want to delete is in the left subtree, like the example 1. I just recursively call this function and put the root left as the new root. That means, for the example, the key is 3. The 3 is less than the root value 5. So I recursively call the function and put the root left 3 to be the new root. Yeah, that means I go to the left subtree and delete the node. The same thing is here. If the key is bigger than the root value, I go to the right subtree and delete the key node. And then we have this situation is a key equals root value. In this situation, I have this this approach. Like this is a root left is none, or the root right is none. The root becomes its left if the root left is not none. The root is root left. If the root left is none, the root is root right. Yeah, that's the.
So you are giving preference for the left subtree.
Yeah.
Okay.
Yeah, that means if the root left is none, the root becomes the root right.
Oh, sorry, you could do it right.
Right
okay,
is
okay.
none. Yeah, the root becomes the root left. Yeah. Okay. And else the root has left subtree and right subtree. I have the transversal node current to be the root right node, and find the leftmost node. When we break the while loop, that means I found the leftmost node, and I replace the value with the root value. And I think that that's the line 32 is very important. Yeah. After I replace the value and the root right, and delete the value of the root right. That means the current value. That means like I'll paste this example. For this example, this is replace the value with 6. There is 5 now. And the current value is 6. And yes, we will continuous to delete 5 for the right subarray. Yeah, that means for this subarray, we continue to delete 5. So to delete 5,
But in this case, you are actually assigning the root value to the current value. So what will happen, I think, is if this was 6 and this was 5, so you're assigning the root value also as 5, and you are not changing the current value, right?
Yeah, current value is always 6 here. Yeah.
So this current value, what you have written here, in 7's left tree as 5, what you've shown here, that should also be 6, right?
You mean what?
No, in this diagram, the below diagram.
Yeah.
Yeah. So this also should be 6.
This is 6. Oh, yeah.
And then you keep on deleting this, right?
Yeah. You keep on deleting the 6.
Okay.
Yeah. Mm-hmm.
So, but then if you come across a situation where the root dash left, okay, sorry, go to the implementation here. When in this, when you are saying that you are actually looking for, no, in the key is equal to root value, the first if, where you don't have a root left is null. So you are assigning root dash right?
Yes.
Root.
Yeah.
So how is this else part going to take care of it then?
This else, the else is root node, root left, and the root right. Yeah.
Okay, so it has to have both of them, right?
Yes.
But when you actually assign that root right to the root, and if the root right, it's both the trees, subtrees are present, then it means it will come to the left, right? Because you'll again go iterating. Or not, you're not going to, okay, you're not going inside. Okay, just assigning it. Okay.
Yeah, this is this situation is to it means the root has only one side subtree.
But you are assigning the root node with the root rights node. You are overwriting that node, right?
Yeah, like this one. If the left is null, I assign the root right to be the new root. If the root right is null, I assign the root left to be a new root.
So there might be some sort of memory leak there. Okay. You're not deleting one of the node. Yeah, it's okay. Yep, I think it's good. Yeah.
You can take not outside and put inside and also. I mean, if not of root of left and root of right, so if either of them is false and not of false is true, it will enter either root of left or root of right. I mean, in line 22, I was saying.
22, yeah.
If you take not outside, then root of left and root of right if you do. I mean, this is an OR operation, right?
This is all. this is all operation. It's all operation.
Yeah.
Yeah. If it's both left subtree and right subtree is noun, yeah, I think it's like yeah. It's also can do that because the root is noun. Yeah.
Yeah, not outside, and in place of or you can put and. Either of is false and not of false is true. It will go there. Yeah.
Yeah. Yeah. Could we move to the next question or discuss?
Yeah, sure. It's fine.
Next. The next question is find k pairs with smallest sum. It's also an interesting question. Well, given a two integer array, nums1 and nums2, it's a sorted array. And also an integer k is given. We defined a pair u and v. U is comes from the numbers 1 and v comes from the numbers 2. The pairs u, v has the sum of the u plus v. So we will find k pairs. That means the ue plus ve is the smallest, and the u2 plus v2 is the second smallest, and uk and plus vk is the k smallest. Yeah, like we have the numbers nums1 and nums2 here, and the output pair. The output pair is, we can see, yeah, this will be more simple. We can see output can be 1 and 2 because the sum is 3. And we also had the 1 plus 4. The pair is 1, 4, have the sum of 5. And we can see is 1 and 6. The sum is 7. And 2 and 7, the sum is 9. And the other pair like the 2, 11 or 4, 7 is much larger than this pair. So the k is 3. That means we only return the k smallest pair. So we return this 3 because it has the k smallest sum. Yeah, that's the question talking about. And then let's go through another example. The nums1 is 1, 1, 2, and nums2 is 1, 2, 3. The k is 2. We have the output is 1, 1. 1, 1 has the smallest sum 2, and 1, 1. The first 1, 1 and the second 1, 1 also has the same sum 2. And if we try other pair like 1, 2, it has a sum of 3. It's larger than 2. So the k is 2, so we just need to return the first 2 smallest pair. So we return these 2, 1, 1 and 1, 1. And for example 3, the numbers 1 has 1, 2, the numbers 2 has 3, the output. Like the U and V must comes from the different array. That means the U comes from numbers 1 and V comes from the numbers 2. So the output, I have several choice here, 1 and 3. This sum is 4. And 2 and 3, the sum is 5. There is no pairs left. It's only 2 pairs because the numbers 1 has 2 numbers and the numbers 2 has only 1 element. So even the K is 3, but we only have 2 pairs. So that 2 pairs are our output. Yeah. Is it clear of the question description? Any idea?
You mean to say how to implement it?
Yeah. Do you have any idea to how to solve this question?
Okay. The very what you say, brute force way would be like, I would do all the combinations of each and every one, and then put it in some sort of a vector or so, and then sort them and just take the first whatever the key elements are. Okay, so yeah, when I'm putting that, it will be something like you'll have a pair of an int with another pair of int.
Yeah.
So the first int will be the sum, and the second pair will be the actual values of those two what you're showing here. Yeah, it will be bigger one array, but I thought that was brute force way of doing it.
Yeah, that.
But not in efficient way though. Yeah.
Yeah. What's the complexity of that one?
So it will be like O of M and N. Yeah, if you're considering that both of them. Yeah. And then you will have to also have a size of like O of whichever is the. It will be the size of the whole. Oh, but it's an output array though, so it should be fine.
Yeah, this is a numbers 1 size, and N is a numbers 2 size. Yeah. Yeah, that's one approach. Yeah, it has a time complexity of the O of M times N. And maybe another approach, it's also the combination pair, but combination pair and use a priority queue or heap. Priority queue or heap.
Oh, you mean to say min heap?
Yeah.
Okay.
Yes.
Okay.
The max heap. Yeah.
Max heap?
Yeah. When the
okay.
Yeah, when the heap size is larger than K, I just pop it out. Yeah, so that means the pair in the heap is my answer. Yeah, this is if heap size is bigger than K, I just pop the max pair. Yeah, that's another approach. Any thoughts?
So if it is a max heap, you will have the maximum sum on the top, right? So when you are actually populating the result value, you will be reversing that array.
Yeah.
Okay.
Yeah, you also can have the minimum heap. Yeah.
Okay. Yeah.
For this, time complexity will be the I think Oh, yeah. Oh, for this sort, maybe we have the combination pair and we have to sort them. It's like
Sorting will be
log. Yeah.
Yeah, but okay. Yeah.
Yeah, log like it's a number of pairs. Yeah. Yeah.
Well, actually, when you are sorting, when you are actually
Mm-hmm.
going through it,
Mm.
so log of n number of pairs.
Yes. This is mn is to get the combination pair.
But it'll be plus, right? But you're not actually doing sorting every time in when you are actually forming that. So m star n plus n log n, something like that, right? Yeah. But then it will again be to mn.
Mm-hmm. Yes, yes. Like yeah, number of the pairs. Like we
So
have.
it will be O of mn. That will be the O notation.
Mm-hmm.
Okay, so in the priority heap, you will still have to go through each and every element.
Yes. Yeah.
No, not of OM. Oh yeah, you'll have to still go through each and every one. Yeah.
Yeah. For the priority queue, I just have the K. That means for the num one, I just iterate K, and for num two, I just need to iterate the K.
It should be K log K, I think. I mean, if it is.
Yeah, that yeah, the K and K, I think it's a K times K. That's the iteration to get the first K pair.
Yeah.
Yeah, that's the K. And then we do the sort.
But to get the K pairs, you'll have to go through the whole list, both the list, right?
Yeah, we didn't go through the whole list because the K smallest pair only in the first K pair.
Okay, so you just terminate when you find the required number of.
Yes. Yes.
Okay.
Mm-hmm.
Yeah, because the array is sorted, so you can take that advantage.
Mm-hmm.
Okay.
Yes. Yeah. And there is another approach that is like this one. And we have this like we find the sum of the two plus everyone, like this is 1, 2, and 1, 4, and 1, 6. Yeah. We can use the first element to pair every element of the array. Like we get the 1, 2, 1, 4, and 1, 6 here. And then we put this pair to the priority queue to get the, oh yeah, another thing. When we put the pair, we have one more variable like the index, the index of the second element. For 2, it's the 0. For 4, it's 1. For 6, it's 2. It's like a tuple. Yeah, you can look at it as a tuple or vector of int. Yeah, that's the same. And put this tuple into the priority queue and get the smallest sum of this tuple. That means we get this tuple here. We get 1, 2, 0.
Index we have to take for both, like for nums1 also we pick whichever element we pick index of that, and for nums2 element there also index, I think we need to take 0, I mean a tuple of 0, 0. For the next one, it should be like 1, 1, 0, 1.
You mean we need another index for the numbers 1? Is that correct?
Yeah, index for like 0, 0, that should be. I mean, index for the 1 also and for 2 also. 2 also.
This one, this for 0.
0 is for second. Here you have taken. For
Yeah.
I mean, for the first element of the num2, you have taken the index as 0.
For this one, we got the this index is for the this index is for the first element. Yeah, that's my fault. Yeah, I'll try to go through it. Yeah.
Okay.
Okay. Yeah, and how we get the 1 to 0, and we pump it out 1, and this is the output. For the output, we got the smallest one is 1, 2. And we got the 1, 2 here, and we find this is 0. Oh, it's not.
Yeah, I was telling you have to take index for both of them, like for first element for here also and for this also.
You mean it's
yeah,
like
yeah,
this?
exactly.
Yeah.
Yeah, exactly. Yeah, 1.
It's 0. It's 1.
Yeah.
2. Yeah. Well, I'll try.
Yeah.
If you add more variable into that tuple, that is fine. Yeah.
Yeah.
Okay.
No, it's
when we pumped out this this tuple, and we find the 0, and when we find the 0, I increase the index of the 0, increase it to 1, and we can get the 7, 2, 1. Yeah. For this example, I just remove the index to make it more simple. Yeah, maybe we can try later. Okay?
Yeah.
Okay.
No.
Yeah. And we put another tuple into the priority queue. That's 7, 2, 1, and put to the priority queue, and we keep pop the smallest one here. It's 1, 4, and we know this 0 is by 1, and we got the 7, 4, 1 here, and we put this to the priority queue and keep popping. Because of 1, 6 is the smallest one, we just got the 1, 6. Yeah. And now that we already have k smallest pairs, then return the array.
I have a question. Why can't we do merge sort? I mean, not merge, but like kind of. Is that because 2 input already sorted, right?
Yeah, the numbers 1 and numbers 2 is already sorted. Both of them are sorted array.
I think my sort will take extra space now, but
because we merge them into one list, but only take k element.
We merge the numbers 1 and numbers 2.
But we actually want the pairs, right? We don't want separate numbers.
Yeah, that's the reason.
Yeah. If you merge them, that you can return the pairs. Yeah.
But when we merge them, the criteria is based on the sum of both value.
That means
I was trying to think if we can use 2 pointers to
Like if you merge them, it's like into one array. But how do you?
No. What he's saying is, when you're merging, you actually do the same thing what you are explaining from the priority queue, right?
Okay, that
Okay,
means
at each and every time you do that and start a merge sort. So the first approach, what we are discussing about, it is slightly similar to that, but he's just saying take the optimum of it. Like whenever you reach a certain K, then you stop. Something like that.
Yeah.
Yeah, but slightly that might also work. But as he said, there will be some additional space to be taken care of.
Yeah. Let me.
But I think the priority queue, the way you are explaining, you are just using only one index. Like
This one.
so yeah, the example what you are just going through 120 140 160. So you are just using one index of one of the array.
Yeah.
So
Yeah.
you are trying to make it more efficient. Yeah. So that also looks good. Yeah.
Yeah.
But I think she should have taken 2 indices. But yeah, that will be okay.
Yeah, maybe.
Yeah, but the only problem here, like whenever you come here, because this example is like that. So when you come at each and every, because you are putting 120 140 160. When you pop out 120, so you will be thinking like 140 will be the least one, but there might be some other element which is also more smaller.
Yeah, we can change that.
So, but then so it is always better to just push one, and then when you pop, you look at the index. So therefore, you might have to take both the indexes also. So you can find all the adjacents, something like the BFS, and then keep on putting them. Just I guess I'm not saying it might be the right thing to do. Yeah.
Maybe I can go through my code and.
Yeah, please. Yeah.
Sure.
Yeah. More ideas. Yeah. This is my code. This is a structure of the compare to make the priority queue to be the minimum heap, because the C++, the priority queue is default max heap. So yeah, in this question, I need the minimum heap. So I create a compare struct, and is compare the sum of the two sum of the pairs. Yeah, this is the sum of the pairs. Yeah, this is a index. Okay, I go so yeah for yeah, we can get this one. This is what I put to the queue. It's the numbers I, that means the U, the numbers 2 is a V, and this is the index of the numbers 2, index of the V, yes. Yeah, maybe this is what I input to the queue.
Yeah, so you're putting all of the nums 2, right?
Yeah.
You're putting all the nums 2.
All the numbers numbers 1 to numbers 2 0.
Okay.
And we put in this while loop, I just pop out the smallest one and put the pair to this is the output array. Yeah, this is pop the smallest one to put to the output array, and we get the T2. T2 is the index of the V, because now the index of V is 0. I increase the index by 1 and put the current index, the current numbers one pair. That means I put the U and the next V and the index of next V to the Q, and keep looking for the smallest pair in my queue, in my priority queue. Yeah. I think it's something.
So why you are putting the T of 0 always? So here in this line 25, so you are pushing T of 0.
T0 is the U. That means like we put the 1, 2. We pumped out 1, 2, and this is 0. 1, 2 is the smallest pair, and the T0 is 1. That means I keep 1 here and go to the next V of the numbers 2.
But every time you are putting T of 0 here, right? So
yeah, every time we keep the U. Yeah, we can show.
Because you don't you want to iterate through the U also? Like you don't want to take the second index sometimes, like that T1 and
T0. Yeah, it's already iterate the whole. Yeah, like we can have these examples. Like
I think once num2 gets over, then she'll go for second element of nums1.
Yeah, we have the
okay,
1, 2, and 7, 2, and we have the 11, 2. Yeah, this is 0. 0. Yeah.
Okay, the one what you're popping out.
Yeah.
Okay.
Yeah, we pumped out this one and increase the index from.
Oh, got it. Yeah.
Yeah, and we push the 1, 4, 1 into the queue, priority queue.
Makes sense. Yeah.
Yeah, and then the 1, 4 is the smallest, and I pop it out and increase the index from 1 to 2, and put the 1, 6, 2 into the priority queue. Yeah, now we can see these 3, 1, 6, 2, 7, 2, 0, and 11, 2, 0. In these 3, the 1, 6 is the smallest pair.
Let's say in nums1, if we had 1, 0, 11, then I think in place of 7, if there is 0.
Yeah.
No, but we need a sorting array there, right? So it will be 0, 1, 11.
Oh, yeah.
We have to.
Yeah, so that is why it won't work.
Yeah,
yeah, that's true. Yeah, that should work actually. Yeah.
Yeah, for this approach is the time complexity is k log k. So it had a better time complexity.
Constant, yeah.
I think it's very special for this question is the 2 array are both sorted, and so we can like keep the merge sort k array. I remember there a similar question in the LeetCode that sorted a merge sorted array, k sorted array. It's something like that. Yeah.
Merge k sorted list, something like that.
Yeah.
That's we use merge sort only in that case. Get the mid and
Yes. Yeah. Okay. Yeah. Yeah. Any question?
No, that's good, I would say. Yeah.
Okay. Yeah. Then I end this discussion session.
Yeah, you just end the recording first.
Yeah.
Yes. I
Yeah,
stop the yeah. Okay. Stop crowding.